Okay, this is a continuation of the 3.1 to 3.6 review lesson from the textbook taken from page 242. All right, this first problem is not going to be too bad. We're looking for relative extrema using the first derivative test. The first derivative test really is nothing more than looking to see what changes you have from your first derivative. If it is a negative to a positive, that means it's going down and up. That'll give you a relative min. If the change occurred from a positive to a negative first derivative, that means you're going up, down. That'll be a relative max. So that really is what the first derivative speaks to. And sign charts are going to inform us about it. So let's get in the business of getting a derivative. So h prime of t will give us 4 multiplied by a fourth is 1, and reduce your power by 1, you get at t cubed. Second term there would be an 8, taking its derivative. Set this equal to 0 to get our critical points. And I know the domain on this original function is x is a member of all reals. So we will not have problems with our derivative not existing. Let's solve for this being 0. 8 goes over, I get t cubed. T equals the cube root of 8, and that makes t equal to 2. This is a critical value for us, and it's our only critical value. Go into a sign chart, and we'll put 2 on our sign chart. On the left and the right, we're analyzing against our first derivative, and here is the first derivative. So take value to the left, let's call it 0, take a value to the right, let's make it 4. Evaluate it. H prime of 0 gives me 0 minus 8, that looks to be negative. H prime of 4 would be 64 minus 8, that would be 50 something. Anyway, it's positive. Doesn't matter what the actual number is, as long as you can tell the sign. Now, when we make our arrows down below, it's speaking to f of x. What's happening to the original function? It has a negative slope, as indicated by the first derivative. So it's a decreasing function followed by an increasing function. The first derivative test would say then you have a relative min occurring at x equals 2. So we have a relative min of, in order to figure out what its y value is, plug it into the original. H of 2 gives me 1/4 of 2 to the 4th minus 8 times 2. That would be 1/4 of 16 minus 16. 1/4 of 16 is 4 minus 16. Looks like this is negative 12, a relative min of negative 12 at, now we can speak to the location at x equals, I'm sorry, it's a t equals 2. Problem is done. Next, be careful taking your first derivative here. They want us to get to points of inflection. I know that's a second derivative. Concavity is also second derivative driven, so I guess the name of the game is let's get to a second derivative. F prime, but in order to get second derivative, you gotta go through first derivative. This is gonna be a 2 times x plus 2 to the first power. Derivative of the inside is simply 1. Then we multiply by the second function there, x minus 4. Multiplication rule has addition between it. Derivative of the second is a 1 multiplied by the first, and that is got a little 2 up there so that we get the squared term. So thinking about how to simplify this, we could, I don't know, I'm one there, I would pull a GCF, so I'm going to do that. I'm going to pull a GCF of x plus 2. That'll leave me a 2 times an x minus 4 because I pulled that x plus 2 out front. Plus, I pulled one of these, I'm going to have an x plus 2 remaining. All right, now let's just simplify in the inside. So I have x plus 2 on the outside multiplied by 2x minus 8 plus an x plus a 2. Those parentheses are not necessary. and we can let them disappear. That gives me an x plus 2 times 3x minus 6, I do believe. Let's go ahead and FOIL this out. I'm going to get, what, a 3x squared minus 6x plus 6x minus 12, giving me a final first derivative of 3x squared minus 12. But it's not really the first derivative we're interested in. We want concavity and inflection point. So that says take it to a second derivative. So f double prime will be a little easier. It looks like it's just simply 6x. Sweet. To find possible points of inflection, we take possible points of inflections. We take our second derivative, set it equal to 0, or else look where it might be d and e. But in this case, our second derivative is a nice polynomial, so don't think we're going to have to worry about d and e's on this. So 6x equal to 0 means that x is 0. I have a possible point of inflection at 0. Go to your sign chart, create a second derivative sign chart, indicating this is second derivative right there. Grab 2 points, a -1, a +1, take it back to your second derivative. So f double prime of -1 would be 6 times -1. That would make -6. This is negative. F double prime of +1 would make 6 times 1, which is positive. We are positive on the right side of 0. All right, do we have a point of inflection? Well, if the concavity changes, we do. And negative indicates concave down. Positive indicates concave up. That definitely shows a shift from concavity being down to up. 0 is a point of inflection. The other thing we can discern is, so x equals 0 is a point of inflection. The other thing we can pick up is that we are concave down on the region from -infinity to our point of inflection 0. We are concave up, starting at 0, moving to the right where we had positive. Okay. 25. Use the second derivative test to find your relative extrema. You can pass on 25. We didn't do the second derivative test to find relative extrema. I pulled 27, but I guess I missed 25. So going to problem 41, find any vertical and horizontal asymptotes of the graph of the function. Use this graph to verify your results. We can wipe out the horizontal asymptotes. We studied that back in chapter 1 and we didn't revisit it in chapter 3. So purely focusing on vertical asymptotes. Vertical asymptotes occur when the denominator is equal to 0. That's the most typical place that you're going to find it. So we're looking for the denominator equaling 0. And on 41, it appears that we will have that situation. So if I've got my numerator, I don't care about the numerator hitting 0. What I care about is the denominator. And if the denominator goes to 0, we are trying to divide by 0. So in this case, x being 4 is a big problem, and it creates a vertical asymptote at x equals 4. Number 42, looking at 42, we're still looking at the denominator, and, 42. We're looking at the denominator here, and my denominator on 42 is an x squared plus 2. Can that ever equal 0? Well, if I've got a positive as such, being x squared, positive plus more positives are hardly ever going to add up to 0. And if I even tried to solve this. I'm trying to come up with x squared equaling -2. Say you even take it one step further and you get plus or minus the square root of -2. This involves imaginary numbers, and our calculus program is solely dealing with the real numbers. So no, there are no vertical asymptotes in this problem. All right, 49 and 50 is the analyzing and trying to sketch a graph. Why don't I just focus on 49 and we'll call it a day. So 49, nice polynomial. First thing I probably would do is get my first derivative. First derivative is 4 minus 2x. And let's find our critical numbers. 0 is equal to 4 minus 2x. 2x equals 4, x equals 2. That is a critical number to me. Next thing I'm going to do is take that into a sign chart so I can get a feel for what's going on around it. Is the function increasing or decreasing left and right of 2? So we pick our test points, maybe 0 and 4. I'm going to rock this into the f prime function, which is right there. Take 0, plug it in. F prime of 0 turns out to be 4 minus 0, which is 4. That's a positive quantity. F prime of 4 turns out to be 4 minus 8. That looks like a negative quantity. All right, that informs us about our original function, f of x. F of x is going to be an increasing function to a decreasing function. We now know that a relative maximum lives at x equals 2, correct? Might even be such that we'll want to get its y value. I think, why don't we take the moment right now and do that? F of 2. Notice I'm talking about the original function f. So we are 4 times 2 minus 2 squared. Gives me 8 minus 4. I get 4. There is 1 point on our graph, and it is at 2, 4. Keep that in mind. Next, let's go into second derivative. Get second derivative information. F double prime of x is equal to a -2. Well, that's kind of unusual. We haven't had that happen too often, and you're probably wondering to yourself, what do I do about that? Well, what I would do is, well, obviously there is not a point of inflection, and the entire function then is got a negative for its second derivative. So throughout our second derivative, our sign chart's going to be concave down. And what else can we get off this? I'm just thinking for my graph. So far we know we've got the point 2, 4. We know it's concave down. We know it's increasing to decreasing. That probably actually is enough. Is it possible to get the intercept points? So y-intercept point says let x be 0, right? Let x equal 0. So if I throw 0 in for x, I'm going to have y equals 4 times 0 minus 0 squared, coming back to the original function. That gives me 0. So when x is 0, y is 0, that gives us the order pair 0, 0. That's a huge help right there. What else could happen? Let's find x-intercepts. X-intercepts is just the opposite. Let's let y equal 0. So let y equal 0 so that it lands on the x-axis. And if y is 0, I get 0 is equal to 4x minus x squared. That looks like a factoring problem. So 0 is equal to, let's pull an x, that'll give us 4 minus x. Either of these two could be a 0. This would say x is equal to 0. This would say x is equal to 4. We already know that from this problem that 0, 0 is an intercept point both for x and y. What about when x is 4? Well, evaluate f of 4. F of 4, take it back to your original function, and it will be 4 times 4 minus 4 squared. 16 minus 16. Big surprise, right? You get 0. The y value is 0 when we put 4 in. So we can plot out at 4, 0 as well. Okay, so I've got to go through these 3 points. I need to do it in a manner where I'm increasing on the left side of 2. So the left side of 2 I'm increasing, on the right side of 2 I'm decreasing. It just so happens that it comes out concave down as it was supposed to. It's a parabola opening downwards. Great. Hopefully I helped you a bit, and do a little more studying. Look over your notes.